Good day everyone. Today, we will discuss about fieldwork exercise number 6, titled Trigonometric Leveling.
So, let me introduce our squad. First is yours truly, Earl, Donde, Loraña. Second is Rennil, Parena, Alsan, Enorme, and lastly, Annielle Joy, Yanzon.
Introduction. Double-rotted differential leveling is a method of determining the difference between elevation between points by employing two routes simultaneously. Two turning points are established such that at each setup of leveling instrument, two sets of independent backside and foresights are taken. Employing double-rotted differential leveling provides a continuous check on process of determining ground elevation while the work is in progress. The method is also useful when there is an urgent need to undertake differential leveling in a short period of time where no established benchmark are available for checking result.
Let's proceed to these fieldworks objectives. First is to acquire and develop the skills of determining the vertical distance, elevation, and height of a remote point by applying the trigonometric and related analysis. Second is to develop the skills of reading vertical angles using the theodolite or the total station. These are the instruments and accessories needed in performing this fieldwork. First is the theodolite. Second is the leveling rods. Third is the markers, it's either chalk or marking pins. Third is the measuring tape, plumb bob, and lastly, range pole.
Procedure. Step 1. Set up the theodolite at a convenient location and call it point A, where the leveling rod and the remote point are visible. Step 2. Using the telescope, take sight at the topmost remote point, then read the vertical angle and record as A on Table 5, Trigonometric Leveling. Step 3. Take another sight for the second trial. This is done to determine the precision of the observations. Step 4. Calculate the mean of the two vertical angles or the angle of elevation, not the zenith angle, of the specified point from the first station. Step 5. Set the leveling staff or rod vertically near the base of the remote point and take the level for sight, i.e. horizontal line or zero vertical angle, on the rod to determine the height of the instrument. Step 6. Transfer the instrument level theodolite towards the location of the remote point and designate it at station B. Then measure its distance by taping from its initial position, which is station A. Record this as distance AB. Step 7. After centering the bubble of the instrument level, sight at the same topmost remote point sighted before twice using the telescope, and record as P on Table 5 trigonometric leveling. After recording these two observations of vertical angle, calculate the mean. Step 8. Level the telescope while at B and get the height of the instrument by sighting the same leveling rod near the base of the remote point. Step 9. Analyze. See figure below. The right triangles formed to determine the height of the remote point. This fieldwork will not consider the effects of the combined correction of Earth's curvature and refraction.
Analysis of the figure above. First, determine the difference in elevation between two instrument setups. Difference in height of instrument is equal to h sub 1 minus h sub 2. Second, consider triangle B'EF, then solve for the distance x using the tangent function. Tangent beta is equal to h sub 1 minus h sub 2 over x. Third, determine the sum of distance AB and distance x for the analysis of the oblique triangle A'FD. A'F is equal to AB plus x. Fourth, consider triangle A'FD and use sine law to determine the distance FD. AB plus x over sine multiplied by the difference of beta minus alpha is equal to FD over sine alpha. Fifth, consider triangle FDG and determine the height of the remote point DG. Sin beta is equal to h minus h sub 1 over FD.
This wraps up the fieldwork number 6. Thank you for listening, guys.